Hi, welcome to this third video on the analytic rank of a tensor. So in this video, we're going to show that the analytic rank can replace the partition rank in some sense. Well, it has some of the properties we showed in the first video that the partition rank has. And so it should be able to be used in the same way the partition rank is used in some combinatorial applications. Okay, so I want to try to put as many, well, I'm going to recall some definitions now. I'm going to go pretty fast because we already had these definitions in the first video. So if you're still confused, you can go back there. But I want to just make this as like self-contained as possible without repeating everything. So we have a tensor, t, and the bias of t is this quantity, x1. It's an average overall. So t is an order d tensor. And chi is a non-trivial additive character. x1 to xd. Okay, but it's also, so it's this expectation, but we showed in the first video, it's also this probability. So xd in v, and it's the probability that this linear form in x1 is identically 0. Okay, so we showed that already. And the analytic rank, if you write arc t, is the negative log of and f is a finite field, the bias of t. Okay, and then we showed in, was it the previous? I think it was the second video, this lemma. If d is greater than or equal to 1, okay, or I guess let d be greater than 1, and for each I subset of d, let Ri from v to the I to R. Remember that as an order d tensor, it's v to the d, right? So is normally what you, so this is an order en order size of I tensor. Okay, and we consider the function. So we define this function R of a vector x to be the sum of all I in D of Ri x of I. So you'll remember this means, so I'm going to write it again, just recall. X of I is equal to the set of all, it's sort of just the coordinates that are in I. Okay, so you remember that from the previous video. So this function, so this is a sum of tensors, and we have the bias, then the bias of R is less than or equal to the bias of the order D tensor. So you have a bunch of order size of I tensors for all I subset of D, but there's only one order D tensor in here, and it's, we're trying to say the bias of R is less than that order D tensor. Okay, so in this section, we're going to show that the analytic rank can kind of replace the partition rank in some applications. And the reason is because, well, we wanted to, well, okay, let's briefly go through why. So when we use the partition rank, we would show that the partition rank is less than something. Okay, and then we show that the partition rank is greater than or equal to the size of A if A is an independent set in T. So I guess T, and A is an independent set in T. And I'll get back to what an independent set is later on when we're just about to prove the thing, in case you don't remember, but it's all also in the first video. Okay, so the first step is to show that the analytic rank of T is smaller than something, and we're actually going to bound it above by the partition rank. All right, so we're going to show that if the partition rank can be used to do this, then the analytic rank should be able to be used to do this too, because the analytic rank is always smaller. Okay, but in real life, actually, there are a lot of ad hoc arguments. I mean, this is usually shown by an ad hoc argument, and in real life, at least when the paper that we're following, so we're following a paper of Shahar Lovett, and at the time of that paper, I mean, there hadn't been any methods. I'm not sure since. I'm sure some people have figured out how to use the analytic rank in and of itself without relying on this partition rank. bound. But anyway, okay, that's all like kind of besides the point. We're just going to show this theorem. So theorem 5, let t from v to d, v to the d to f, be an order d tensor. Okay, then analytic rank of t is less than equal to the partition rank of t. Okay, and what's the proof? So we spent a whole video proving subadditivity just so we can do this. So by subadditivity, okay, we can assume that t has partition rank 1. All right. Why can we do that? Because so we're gonna assume that the partition rank of t is something, and we're gonna show the analytic rank is less than that. And to do that, I mean the analytic rank. So say t has partition rank r. So if t has partition rank r, then t is equal to t 1 plus all the way up to t r for some partition rank 1 functions. And so arc of t, right, arc of t, which is equal to arc of this, is less than equal to arc of t1 plus all the way up to arc of tr. So it's just suffices to show that arc of a partition rank 1 function is less than equal to 1. Okay, I'm going to erase that mess. If I can figure out where the eraser is. Is that the eraser? Nope, that's a highlighter. Okay, let's go like this. Sorry about this. I don't know how to use my technology. Okay. And then let's go back to. If I can't get back to a pen, it's going to be really unfortunate. Sorry about that. Okay. So I figured out how to get my pen back. Now we want to show that. So we assume that t factors. So now t is assumed to be partition rank 1. So t is equal to t. I guess let's write this out. All the variables. So t of some vector x. Okay, it factors as t1 x to the x of a. Not plus, it's factors, times t2 of xb, where a union b is equal to d. So my thing's really tiny now. So a is not empty, and b is not empty. Okay. So we shall show that arc of t is less than or equal to 1, which is equal to the partition rank of t, by showing that bias of t is greater than or equal to 1 over size of f, right? Because the analytic rank is the negative log of the bias. Okay. So for a, b, and f, okay, define this function. The function f sub ab of x to be t1 of x plus a, t2 of x plus b. Okay. Now let's rename all these little. I mean, there's 4 terms in here. Let's rename these terms. So let's call r d. What's that? Let that be t. R a is b t. Oh, sorry, this is x a. This is x b, because otherwise it wouldn't make sense. T1. So RA takes, a vector indexed by A, and T1 happens to be indexed by A. RB is A times T2. Our empty set is equal to AB. And so those are all 4 terms. and then Ri is equal to zero, the zero tensor. I'll write 0 for all other I. Okay, and so if we do that, then we see that R of x is equal to FAB of x. And R meaning, R in this, in the language of lemma 2 here. Okay, so what does lemma 2 say? So lemma 2 says that the bias of FAB is less than or equal to the bias of T. Okay, but on the other hand, we have, if you take the expectation AB in F of bias of FAB, okay, this is the expectation over AB. If we just unravel the definition in F, expectation over X in V to the D, chi, and then we write it out, right? T1 of X plus A, T2 of X, this is XA, XB plus B, and all these brackets. Okay, and that's equal to, right? Okay, so here's what happened when we took the expectation over all x. Anything that has an x in it just disappears, right? Because you have the average of something over well, it's chi, so it goes into the complex numbers, but it's still a finite, it's a finite group, right? And you have the average of something over a finite group, and it's going to be 0. So that the only thing that survives here is the term that doesn't have an x in it. And so that's expected value of AB in F of chi of AB. Okay. And so that's the probability that, so this is going to be non-zero if this is going to be non-zero if B is equal to 0. So it's F probability that B is equal to 0. Okay, and that's 1 over the size of F. Okay. Yeah. Meaning, sorry, like if you pull the A inside that thing, the expected value overall A of chi of AB is non-zero when B is equal to 0. So that's what I meant to say there. Okay, so we may find A, B such that bias T is greater than or equal to bias F AB, which is greater than or equal to 1 over size of F, and that's all we need. All right, so we've shown that the analytic rank is less than the partition rank. All right, so where does that bring us? So now we want to prove a lower bound on the analytic rank in terms of an independent set in T. And I'm not going to, if you remember what an independent set is, that's great. Right now, I'm still not going to define it because I just want to define it right before we use it. But we need a lemma. So to show, before we can show that lower bound, we'll need a lemma. What am I at, 6? That says that the analytic rank does not increase when you restrict to a subspace. Okay, so let T from B to the D to F be an order D tensor, and let U subset of V be a subspace. Okay, so if T restricted to U, that's the notation for that, is the restriction of T to U, then the analytic rank of T restricted to U is less than or equal to the analytic rank of T. Okay, so restricting is not going to increase the analytic rank. So proof, let W in V be a subspace such that it's the complementary subspace. So you direct sum W is equal to V. And so any V has a unique representation as V equals U plus W for U in U, W in W. And so the bias of T, so bias of T is going to be equal to this expectation. So U1 all the way up to UD in U, and then W1 all the way up to WD in W. Chi of T of U1 plus W1 all the way up to UD plus WD. Okay, we just wrote V as U plus W. Here. Okay. So now you fix an arbitrary choice of W1 all the way up to WD and W. Okay. And we see that, I mean, this was kind of, we went over this in the previous video, but U1 plus W1, UD plus WD, it splits as this sum over all I subset of D. Ti, Ui, Wi complement. And so what is this? If you'll remember from last video, we use a similar notation. So Ui, Wi complement is equal to T of Z1 up to Zd, where Zi is equal to Ui if I is in I, and Zi is equal to Wi if I is not in I. Okay? And that makes sense, right? Because by multilinearity, you need to pull out, you pull all the summands apart in every possible way. This is every possible way. Okay, so where am I at? Okay, so by lemma 2, okay, this is exactly how we need it, right? Because each of these is an order I tensor. If we fix W1 up to WD, this is an order I tensor in UI. So by lemma 2, okay, the expected value of the expectation of U1 up to UD, or sorry, overall U1, UD, and you take this chi of TU1 plus W1 U D plus WD, okay, is less than equal to, it's less than equal to the expected value of U1 UD, just the top one, right? So the top tensor, the order D tensor here, which is just T. So chi of T U1 up to UD, right? I mean, this is not U1 plus W1, right? It's actually U1 because we don't take the W's at all. Okay, and this is just equal to the bias, and that's how we managed to restrict it to a subspace. So the bias of T restricted to U. Okay, so this is for all, I mean, this is for all W1 up to WD, so we average over all W1, WD, and W. And you apply the triangle inequality, so we get bias of, well, you don't even need to put the bars yet. So bias of T is less than or equal to where you put the bars, right? And then you average over all W1 up to WD here, right? Add an extra average. And once you pull it inside, you get the thing on the top here, which is less than or equal to bias T. Okay. So we've shown that, we've shown that the bias of T is less than or equal to the bias of T restricted to U, which means that the analytic rank you flip it's the negative log, right? So you flip it around and you get the analytic rank of t restricted to u is less than the analytic rank of t. Okay, so now we're going to prove the last result, which is that the analytic rank is bounded from below by the size of an independent set up to some constant factor. So, well, it's constant factor depending on d and the size of f. Okay. So so what's an independent set? An independent set in T is a subset. So I mean, we're going to regard T as from f to the n, as a function from f to the n to the d to f. Okay, I mean, you could take, instead of to the n, you could take it to any set x. That's what we did, I think, in the first video, but let's just say that x is 1 through n, is a subset of this index set, kind of the subset A of this index set, but it could be x, right? Such that for all I1 up to ID in A, okay, in the subset of the indices, the coefficient indexed by I1 up through ID is non-zero, not anti-set, sorry, non-zero if and only if I1 is equal to ID, meaning that if you restrict to the indices in A, you kind of have a diagonal tensor. Okay, that's an independent set. And we want to show, so this is what we want to show. So theorem 7. So remember, for the partition rank, we were able to show that the partition rank of T is greater than or equal to the size of A. But we're only, if we change this to an analytic rank, we can only show it's greater than C times the size of A. And what exactly is the statement? So theorem 7, let T from f to the n, the d to f be an order D tensor. Assume that A subset of n is an independent set in T. Then the analytic rank of T is greater than or equal to C times the size of A, where, okay, C is this, it's minus log base the size of F of 1 minus 1 over the size of F to the D minus 1. That's it. And then we have some observations, so that C is greater than or equal to 2 to the minus D, and C is greater than or equal to 1 minus log D minus 1 over log of F. Okay, so let's prove this. So we let S be a tensor from F A to the D to F, be the restriction of T to F A. So this is going to be a subspace of F to the N. And by the previous lemma, the analytic rank of S is less than the analytic rank of T, so we are done if we can express the analytic rank of S as a function of size of A. Well, in particular, we're going to show it's a constant times size of A, where the constant is above. Okay, so the bias of S is equal to this average, right? x1 up through xd in f to the a of chi of, but because we know that it's diagonal in this way, right? It's just the sum over all I and a of ci times the product of j in d of xij, and xij is the jth coordinate of the vector xi. Okay, because it's non-zero if and only if it's on this diagonal where all the xi's are the same, or the x1 through xd are the same. So yeah, I think you know what I'm trying to say. Okay, this is going to be the same, and so it's like a one-dimensional sum instead of a many-dimensional sum. Okay, so then but so now we also have, right, remember what we said about it's actually a probability. So bias of s is equal to the probability if we fix x2 through xd in f of a, okay, that the linear form is non-zero. And when is the linear form so not identically zero? Well, that means for all I and a, okay, this coefficient xi2 xi d is equal to 0. Okay. Oh, sorry, it is identically 0. So it's the bias is the probability that it's identically 0. And where did I say that? Let's just make sure. Recall. Yeah, it's the bias if you fix x through to xd that this thing is identically 0, has a linear form of x1. Okay, so it's a linear form. So it's an identically 0 if this holds. And you can just see that this is easily seen to be. So we want, it's 1 minus the probability that all of them are 0. So 1 minus 1 over size of f d minus 1, and that's this inner thing, and then we take the product over all of them because they're independent. Okay, so I mean, why don't we stare at this for a while? Right? So this inside, we want all of these to be 0. xi, j to be 0. That's 0 with probability that. Want all of them to be 0, and sorry, wait, what am I trying to say? We don't want all of them to be. Okay, sorry. Why don't we stare at this a little bit longer, because I seem to be confusing myself, so we gotta make sure that we did this right. So the product is 0 unless one of them is non-zero. Okay, and so one of them not being non-zero is this. Right here. Okay. I think I convinced myself. Okay, so by convexity, so there's a convexity argument for d greater than or equal to 2 that c is greater than minus log base 2 of 1 minus. You're basically changing this to 2, and because it's as a function of f here. Oh wait, what am I trying to say? So sorry, like I missed a step, right? This is the bias of s is equal to that. So you take the negative log of this, and you get that the arc of s is equal to c times size of a. Because you take the negative log of this, a drops down, and c is just that. It's the negative log of this inside here. Okay, sorry for not saying that. And so c is greater than or equal to minus log of 1 minus 2 to the minus d minus 1. Okay, because as a function of f here, it's convex, right? Negative log is convex, and then this is also convex. 1 minus log base f. Oh, sorry, what am I writing? This is greater than or equal to 2 to the minus d minus 1. Okay, and also you can check that C is greater than minus log of, I guess if F is greater than D. Okay, it's log to the size of, log base size of F, D minus 1 over F equals 1 minus log base size of F, D minus 1. Okay, I mean, this is not super important. Well, I mean, it is kind of important in applications. You want to know that C is not going to be like that close to 0. And it's not going to be that close to 0 as long as the size of the field is pretty big. And there's this like unconditional sort of bound right here. No matter the size of the field, if D is greater than 2, which is when we even care about tensors, then it's not going to be smaller than a half to the power D minus 1. Okay. And so that ends it. That shows that the analytic rank is at least as useful as the partition rank. I guess if you don't mind this constant C here, but you usually don't, right? I mean, because for example, in the partition rank, the use of the partition rank for the capset problem, if we just put a C in the A, it wouldn't have changed the exponential bound, at least I don't think. Okay, so that's the end of this video. I hope you enjoyed this video in this series, and I'll see you next time.